Welcome to This Explainer. Today we're jumping right into a totally fascinating and maybe slightly intimidating corner of advanced calculus to investigate a very specific equation, the Bessel function. If you've ever stared down a massive string of mathematical notation stretching off into literal infinity and wondered how it actually behaves, well, you are in the right place. We're going to break it all down step by step and figure this out together. So let's dive into our central question for today. How do we mathematically prove that a series going on forever doesn't just, spiral completely out of control? I mean, when a math equation involves an infinite sum, it's constantly adding new terms, forever. Our goal today is to tame this specific infinite series and pin down its exact interval of convergence. We want to discover exactly where it behaves itself on the number line. Here is our incredibly logical, investigative roadmap for this exercise. 1. We'll meet the Bessel function. 2. We'll prove its interval of convergence. 3. We'll differentiate it term by term. 4. We'll compare those intervals. And 5. We'll see exactly why factorials always win. All right, let's kick things off with section 1, meeting our mathematical suspect, the Bessel function. Okay, this is the Bessel function, usually denoted as j sub 0 of x. Now, I know it looks pretty daunting at first glance, but let's just break it down. We've got an alternating infinite sum starting at n equals 0. On the top of the fraction, the terms are going to alternate signs right alongside x raised to the power of 2n. And on the bottom, notice this massive denominator featuring the factorial of n squared. Every single piece here is going to play an absolutely vital role in how this behaves, and it sets the perfect stage for the mechanics we're about to uncover. Moving right along to section 2, proving the interval of convergence, which is our investigation for part A. To solve this case, the ratio test is going to be our ultimate magnifying glass. It's honestly perfect for equations packed with heavy factorials and exponents. We just set up the ratio, dividing the n plus 1 term by the nth term under an absolute value, we simplify the fraction, and then we take the limit to see exactly where it falls below 1. So, the absolutely crucial point here is applying this clever algebraic trick, which lets us cancel out the massive factorials in our ratio. By recognizing that the factorial of n plus 1 is literally just n plus 1 times the factorial of n, we can just cross out the matching terms. It is so incredibly satisfying to do, and it completely clears out the visual clutter of the equation. It leaves us with a much cleaner path forward to evaluate our limit. After simplifying, crossing out our negative signs because of the absolute value, and canceling all our factorials and exponents, we get this beautiful, clean fraction, x squared divided by 4 times n plus 1 squared. This sets us up perfectly for our final calculation. All the intimidating, scary parts of the Bessel function have just been distilled down into this highly manageable expression. Now, taking the limit as n approaches infinity, we find that for every fixed x, that massive n in the denominator completely dominates the fraction. The whole thing just shrinks away, giving us a very satisfying limit of exactly 0. And because 0 is for sure strictly less than 1, the test proves the radius of convergence, or r, is infinity. This means the interval of convergence covers all real numbers, from negative infinity all the way to positive infinity. Seriously, no matter what number you plug in for x, this infinite series will always settle down to a finite value. Our mathematical suspect is perfectly well-behaved everywhere on the number line. All right, section 3, differentiating term by term. This is our investigation for part B. So what actually happens to our infinite sum when we apply a little calculus? Well, we differentiate term by term using the good old standard power rule. The 2n simply comes down in front, reducing the exponents, and after a bit of quick factorial maneuvering to simplify the coefficients, we land on a brand new infinite series for the derivative. It's a really fantastic demonstration of how linear operations can just easily slide right inside a summation symbol. And this brilliantly illustrates that shift. If we compare the first few terms, we can see exactly how the derivative transforms the original function. The original Bessel function starts with 1, then subtracts x squared over 4, and so on. But the derivative starts directly with a negative term, negative x over 2, plus x cubed over 16. The structure is totally similar, right? We've got alternating signs, increasing powers of x, but the actual terms have fundamentally changed to reflect that new rate of change. Which brings us to section 4, comparing the intervals for part C. The big question now is, does this new derivative series still behave itself across the entire number line? Or did taking the derivative introduce some kind of instability?
Well, we pull out our ratio test magnifying glass one more time, applying the exact same 3 steps to our new derivative function. We set up the ratio using our new terms, which we'll call b sub n, and after running through the same algebraic factorial tricks, we arrive at a newly simplified limit expression, x squared divided by 4 times n minus 1. And exactly like before, the limit calculation yields a resounding 0 for every real x. Because we still have n times n plus 1 sitting down in the denominator, it completely explodes in size as we approach infinity, forcing that limit straight back to 0. Looking at our final answers side by side, we have definitively proven that both the original function and its derivative share the exact same infinite interval of convergence, all the way from negative infinity to positive infinity. Differentiating the series term by term obviously altered these specific values, but it didn't disrupt the fundamental stability of the series at all. They both perfectly converge everywhere. Finally, section 5, why factorials always win. Let's get to the ultimate truth of this whole thing. What's really interesting here is that the limit was actually a race between the exponents on the top and the factorials on the bottom. When you look at the raw equations, the top of the fraction is driven by x to the power of 2n, which is growing fast. But the bottom of the fraction, it's driven by n factorial squared. It's a literal mathematical race to infinity. In this mathematical battle of David versus Goliath, the factorials in the denominator are always going to grow infinitely faster. Exponents are powerful for sure, but factorials are the true mathematical heavyweights. Because they completely outpace the powers of x, the denominator dominates the entire expression, tending to infinity and driving the whole limit down to 0. That is the underlying architecture that guarantees our Bessel function stays perfectly behaved. So, knowing this hidden power dynamic, how are you going to approach your next complex calculus problem? The next time you look at a terrifying infinite series, don't let the notation overwhelm you. Look for the structure. Look for the factorials. Remember the fundamental truth we uncovered today. In the race to infinity, the factorial is absolutely always the safest bet. Thank you so much for joining me on this explainer. Keep questioning, keep simplifying, and I will catch you in the next one.